title of my talk, it's going to deviate slightly from what you said. I'm just going to do a sort of an overview of one of the subtasks, which is bifacial PV on trackers. There's been a lot of overview. I'm going to try to go into one task and the report we're planning, but it's still difficult to cover everything, even in one presentation. So the work I show today is not done just by myself, but some of my co-authors here I'd like to acknowledge, especially the subtask leaders. So that's Josh Stein from Sandia Labs in the US and Josue Malgeri from RSE in Italy. All right, so bifacial PV on trackers is actually two technologies. It's bifacial PV and it's trackers. So if you went on the technology tour today, you probably saw a lot of bifacial PV and some trackers. So I thought I'd just take a bit of time to break the two down. So this graph in blue shows the total cumulative PV capacity. I think Ken showed something similar as well as Fleming. So the blue curve is not new information. But what is new information is the red curve on the bottom. So that's showing the approximate percentage of bifacial PV. So what percentage of the installed global capacity is bifacial PV? So at the end of 2022, we think it was about 11%. And so what you see is that it's grown from essentially 0% to that in a very short time. So there is a distinguishing feature between bifacial cells, which is a silicon cell typically, with the backside metallization sort of removed. And it is totally possible to put a bifacial cell in a monofacial module. So it's not that easy to figure out how much of the global capacity is bifacial in that sense, but a true bifacial module will typically have glass on the front and glass on the back. What's the reason for this uptick in bifacial installations? It's the bifacial gain, as well as the costs have come down on the technology. So typically at utility scale, energy gains, when I say gain, it's compared to an equivalent monofacial or single-sided system. It's going to be about 5 to 10%, depending on a few things, largely the albedo, which is a Latin term meaning whiteness. So if you have a really reflective surface, such as snow or a white material, yeah, you can crank up the gain to in around the 20%. And then, of course, depends on the layout, how dense the rows are, and how much they're shading the ground. And then it's also dependent on the cell technology itself. So the workhorse of the bifacial era has been the PERC cell. And that has what we call bifaciality. So it's the back to front side efficiency ratio of about 70%. So the back is about 70% efficient as the front. But that's changing now with more interest in N-type materials. So N-PERT, you can get a bifaciality of closer to 80% and higher still with silicon heterojunction technologies. So I think that's going to be the next generation of bifacial. And so the bifacial gain is additive to the tracker gain. So let's talk a bit about trackers. There's quite a few different types of trackers. By far, the most common type is the single axis tracker or the horizontal HSAT tracker. It's called that because the axis is horizontal on the ground. You can also have TSATs, which would in this hemisphere tilt the axis towards the southern direction. That's not so common. But at utility scale, it's this horizontal single axis tracker that typically will rotate from east in the morning to west in the afternoon. That's what you saw on the technology tour. You can, of course, rotate that axis 90 degrees so that it's east to west and the modules tilt from north to south, but that's not so common for PV applications. That was more of a CSP era thing. And then you can have dual axis trackers where the rack is tilting in elevation and azimuth. And in that case, even though you can get energy gains in the ballpark of 30 to 40% higher than a fixed tilt design, the structure cost is a lot higher on a dollar per watt peak basis. And it's also really hard to pack in a lot of these structures within a given area. So that's why the single axis tracker is the most common. So that's what we're studying in this report. This is a common tracking profile, so how the tracker will orient itself over the course of one day. The colors show different algorithms for different ground cover ratios. So that's how packed in the rows are. So what you see is that negative angles mean rotated towards the east. So it starts out not going to the most extreme angle, because if it did that, they would shade each other. There would be row-to-row shading. So the trackers actually backtrack is a very standard thing in this period here. And then once it's reached the end of its backtracking phase, it goes in, they all go to what you call true tracking. So it's really trying to minimize the angle of incidence between the sun's beam component and the array. So that's a very standardized tracking algorithm. And what we're seeing is a lot of tracker manufacturers have tweaks to this algorithm. There's a lot of ways you can interrupt this algorithm. So we know that all the good PV sites are sort of taken now. We're building more on complicated terrain. So how do you account for that? You're going to adjust this algorithm. It's also designed, this algorithm, for the beam component. So when it's sunny. Right now, it's almost completely cloudy, so the ideal position for a tracker would be closer to horizontal. And when and the decision how to make that move from this position to a horizontal is not that trivial, and different manufacturers have different approaches. We talked about extreme weather, so if there's hail, you might want to go to a steeper tilt to avoid that impact energy. Some tracker manufacturers have flood sensors, and trackers will go to horizontal to preserve the panels. So. And there's snow and soiling removal modes, and so it gets quite complicated. So that's what we're highlighting, some of these challenges and best practices for implementation in our report, and that's due out in summer 2024. So there's going to be a bit about optimizing the yield with layouts and what the industry and research has learned about albedo optimizations. We're going to have a whole section on modeling practices, and we've done a intercomparison that I'll show you a few results from. We've done a industry-wide survey. I'll show you some results from that in a bit. And we're doing another survey right now on for users. So project developers, we know that trackers don't always work as expected. So we're trying to get an overview of the most common reliability issues. So I want to talk a bit about the modeling comparison that we did. So we invited modelers from industry and academia to model this system that you see here. It's a 5-row, this is an aerial view of a 5-row tracker system. And we asked modelers to model the center module and the 2 edge modules that you see in green there. So it really required a 3D tool to do this modeling. These are just some details of the modeling scenarios. There were 7 scenarios listed here in the rows. And what's different in each one is highlighted in red. So we did some variations in the ground cover ratio, the albedo, the height of the tracker. What I was most interested in this case was actually scenarios 5 and 6, which was simulating trackers on sloped terrain to see how well or how much. It wasn't an absolute accuracy comparison. It was really to see how we compare to each other. So I'm going to give you 2. So there's a lot of steps in the modeling process as you go from, let's say, photons in the sky to the electrons on the grid. There's just a lot of loss factors you need to account for. So I'm going to show you just 2 steps of the modeling process. One where we're doing pretty good as a community, and one where we need a lot of improvement. So the first one where we're doing okay is on the tracking angles themselves. So we got 7 participants coming from various segments of industry and academia. So the different squares here are different days of the year. And this is for a reference case. So you see the slopes here really represent what I showed on one of the first slides. And since most of there's very little variation is what you see, except for at the very beginning and the very ends of the days. So that's backtracking. So it could be something with how the modelers are calculating sun position, could be something different about the backtracking algorithm itself, but that seems where we have the most discrepancy. But we're mostly doing okay there. What we're not doing okay is on the rear irradiance calculation. So again, this is one tracker geometry, but 5 different days shown here. So it's a collection of sunny and cloudy days. And there's significant variations among these 7. I won't go into the details about the models that were used. There's different approaches to do this. But it's clearly some room for improvement on what we mean when we say we're doing rear irradiance modeling. Funny thing about these results is that because the rear irradiance is a fairly small, like I said, 5 to 10% of the total picture of total irradiance front and back, you can be sort of out to lunch on your rear irradiance predictions. And as long as your front side irradiance predictions are okay and your cell temperature predictions are within reasonable range, you can have a fairly accurate energy yield model despite having rear irradiance predictions that are not. So this is the effect of slope. So this is scenario 5. So what you're looking at here is for the 7 different modelers, the difference in their reported angles of the reference case, which was flat terrain, and the sloped terrain towards the east. Ideally, what you would see in the morning for a sloped terrain towards the east is that the trackers would tilt a little bit more into the sun when the sun is down slope, and then they would have to backtrack a little bit more in the evening. And we see that to a large extent, except for 1 or 2 models that just don't seem to be accounting for this sloped effect. So we're going to report a little bit more on that as to why. And then this is the front side irradiance for the same slope scenario. So we can see in the morning, most models do have a boost in the front side irradiance due to that tilting into the slope, and then less irradiance in the afternoon due to the heavier backtracking. All right, I just want to give you a few details on our company survey, wrapping up pretty quickly before coffee here. So we surveyed 17 companies from these countries here, so most of them in China. So yeah, we talked about cells, wafers, polysilicon modules, most of that coming from China. It seems that a lot of tracker manufacturers are also based in China, but there's a lot of tracker manufacturers located in other countries as well. Out of all these companies, we believe that we captured about 80 to 85% of the total market in our survey. So here's just some really high level breakdowns. On the left, it shows what tracker offerings there are amongst these companies. There was only one of the companies offering 2-axis trackers, so it does really seem to be a technology that's fading away. By far more common is the horizontal single axis tracker. There's different ways you can configure a single axis tracker. You can have modules in portrait, modules in landscape. But what the graph on the right is showing that the 1P, that's one module in portrait, is by far the most common product offering. And that's likely due because it's on a cost per watt peak basis. It's just cheaper than at least the 2 in portrait options. So back up. One of the complaints about the IEA reports has been that they're too long. So in this round of reporting, I've been told that we have a 50-page limit. So to do that, we're going to have to pack a lot of information into a small area. So I talk about an ink to information ratio on graphs. So the ink to information ratio is going to have to be quite high. This is my attempt at one of those ratios. So we asked tracker companies, I think, over about 40 questions. So this encapsulates 4 of those questions. And what you're looking at is, so honing in on one of their product offerings of each tracker, saying, what's the max row length of the tracker versus what's the max north to south slope? The north to south slope is typically the limiting factor for trackers. The east to west slope is not so limiting. And then the colors show how the tracker is being powered, whether that's from a small PV panel or from the grid. And then what is the max tilt angle is the size of the marker. So there's some interesting things that we can see on a plot like this. So one is that if you look at the 15 degrees and just draw a line vertically, most tracker manufacturers say that's the hard limit for installation. If you want to install in steeper terrain, you're going to have to grade it. We also see sort of a negative correlation with the length of the tracker and the slope that it can be mounted on. So particularly noticeable is that dot in the bottom right-hand corner where the shortest tracker length can actually go to a 30% slope. Most tracker manufacturers, looking at the size now of the markers, have a tilt angle between 55 and 60 degrees. We did note that there was 3 manufacturers that we interviewed who have a tracker that can go to 90 degrees, which is only for agricultural PV applications. So when you're doing sowing or harvesting. It's not for continuous operation. So we have a lot of information like this that we're going to put in the report. And so to conclude, bifacial plus tracking, I think that is going to just increase in market share. Many of these companies that we interviewed have modifications to the standard tracking algorithm that does make it hard to model because we don't always know exactly what they're doing. I showed that the modeling community needs to improve on its rear radiance, at least in the way we agree upon what rear radiance modeling is. And yeah, so you can expect our report at the probably mid to late summer 2024. So thank you for your time.